Hello all and welcome back to this course on digital systems. The last lecture we were looking at the concept of a hierarchical design where we use components that we already built, right? Blocks that we already built in order to implement more complex blocks or in some cases even simpler blocks, right? So now let us, and in particular we looked at the example of a decoder, a 3:8 decoder, on how it can be used to build 7:128 or 2:4 decoders and so on, right? Even the concept of the output, number of outputs not being a power of 2, we also looked at. Okay, anyway, so let's now proceed to another important hierarchical design, which is basically the multiplexer. Right, the multiplexer essentially, if you remember, the basic idea was to allow one of the 2 power n inputs to go through to the output, right? And therefore we have n select signals, and that was the idea there, right? So the symbol of a multiplexer, so maybe I will consider the base multiplexer that I build, okay, to be one of I0, I1, I2, I3. So I'm going to consider 4:1. I1, I2, I3. Okay. So for this I need 2 select lines, S1 and S0. Okay. And the multiplexer always has only one output, Y. Okay. So this is going to be 0, 0, 0, 1, 1, 0, 1, 1. Right. And S1, this is the LSB of the select line. Okay. So which basically means 0, 1 combination will allow I1 to go through, 1, 0 will allow I2 to go through, right? And we also looked, again let's remind ourselves that the standard cell library we are talking about, is basically an inverter, okay, then a bunch of AND gates, 2 input, 3 input, 4 input, right? And then you have OR gates. Okay. This is our standard cell library. Okay. Now the idea is, this multiplexer, of course, we were able to say that, y, in terms of Boolean expression, S1 bar, S0 bar into I0 plus S1 bar, S0 into I1 plus S1 S0 bar I2 plus S1 S0 into I3. Okay, and this was very easily implementable with just 3 input AND gates. And of course you needed the true and complement of the select lines, right? And we basically, either we could do the tri-state inverter logic, right, which could allow us to do a wired OR connection. Okay, so that's an important addition to the standard cell library if we were to go ahead and add it. Okay, what is that? We have not just an inverter, I have the standard inverter here. I am going to add the tri-state inverter to this standard cell library, so that the multiplexer implementation becomes easy. Okay, so we had already looked at the Boolean implementation, right, using standard cell gate shown here. So I will not get into that part again. Okay, so let me just redraw this nicely. 4 inputs. Yeah. Okay. Now what we notice is that it is indeed, if you look at these expressions, right, Okay, and suppose I had a 2:4 decoder. Okay, which basically had my select lines S1, S0, 1, 2, 4, right? This is Y0, Y1, Y2, Y3. If you look at this expression here, it is nothing but S1 bar, S0 bar. Okay, it's just the min terms S1 bar, S0, S1, S0 bar, Y3 is S1, S0, right? Therefore, this particular, let me just call this MUX. Y MUX can be written as Y0 into I0, Y1 into I1, Y2 into I2 plus Y3 into Y3 into I3, right? Now, therefore, this seems to suggest that we can now use a decoder to actually implement a multiplexer. Okay, so what do I have to do? I simply say, okay, this is my 2:4 decoder, okay, with select lines S1, S0, and remember, okay, we'll also have an enable here. Okay, we'll see what that should be tied to. Okay, and then we are going to say that the output, okay, so this is S1, S0. Each of these I am going to now AND with I0, I1, let me draw this a little better. I2 and I3. Okay, this is my Y0, Y1, Y2, Y3 of the decoder, right? So I can now do one of two things. I put this entire thing through a 4 input OR gate. Remember, that's available in my standard cell library. So I will do this. Okay, and I get my MUX. So this is done, right? So this is very neatly done here, and I have essentially given that I had already made a 2:4 decoder. All I needed is just one OR gate, right, to get this multiplexer going, right? In general, if I wanted to make a 2 power n is to 1 MUX, right? That is basically a very large MUX here. Okay, I0, I1, I2 power n minus 1. Okay, this is not 2 power n minus 1, it is 2 power n minus 1. So I have 2 power n inputs and I have a single output Y MUX with, of course, n select lines S0, S1, Sn minus 1. Okay, so this is a 2 power n is to 1 MUX. Okay, so in general, if you wanted to implement this kind of a multiplexer, you would have to do the following, right? You need, first of all, an n is to 2 power n decoder. Okay, why? Because these select lines S0 to n minus 1, right, essentially need to basically select one of those 2 power n outputs, right. So I can just write that. So I'll just put the select lines below, right, S naught, S1 all the way to S n minus 1 Y MUX, right, and those are the select lines. And this enable that we usually have in the decoder, I am going to connect that to 1, logic 1, okay, or in terms of voltage I will connect it to the power supply. Okay, I am going to connect it to logic 1. Okay, why is that? Let's go back to this implementation. Here also I am going to connect it, this enable I will put it on top, right. I am going to connect it to VDD, okay, or logic 1. If you did not do that, what will happen is y0, y1, y2, y3 will all be 0, right, and the output of the MUX, y MUX, will end up being 0 because it's an OR gate there. Now you do not know if it is 0 because the inputs happen to be 0, right, or you know, I0, I1, I2, I3, or one of these inputs were 0, or whether it's y MUX is 0 because the you know, none of them happen to be selected, right. So therefore we would like to, you know, differentiate between the two and be careful about it. So the enable we will just try to 1, and you know, we'll say that therefore the decoder, one of the outputs y0, y1, y2, y3 have to be high, and the output y MUX can be high if and only if one of the inputs, depending on which one is selected, is actually a logic high, right. Otherwise basically it has to be a 0, right. So therefore this also I will just, the enable I have connected to logic 1, I get a I don't get a MUX, y MUX here, I am sorry about that. I have y0, y1 all the way down to y2 power n minus 1, right. Exactly, right. So this is what I have, n inputs and 1 of 2 power n outputs, right. And then what I am going to now do is, of course, you know, I can put an AND gate with each input I0, I1, I2, I3 and so on, and put like a huge OR gate, a 2 power n input OR gate, or I could do it with a tri-state this thing. So what I'll do here, I'm just going to this is I0, this is Y0, right. So in some of these places we, you know, if the drawing can get cumbersome, right. So let's see, I1, Y1, right. This is, sorry, I2 power n minus 1, right, and this is y2 power n minus 1, okay. And now what are we going to do? We are basically going to say, you know, you can put a huge OR gate here if you want it, right. That's what I told you, okay, and you will get the output. Alternately, the better way to implement this is to obviously replace you know, this. So let me just complete this diagram. So let me call these outputs as y0 prime, y1 prime, y2 power n minus 1 prime, and then the inputs to these OR gates are like this, y0, y1, y2 power n minus 1, right. So sometimes if this drawing, see, if I were to draw a line like this to every input, it can get a little cumbersome, right. For that reason, sometimes these labels can be used in order to just represent the same thing. It's so this y0 here is the same as this y0, this y0 prime here, let me put it in a different color, y0 prime here is the same as this y0 prime and so on. So this y0 prime is the same as that y0 prime, right? So this is an other way, an equivalent way of drawing the same schematic without drawing every single wire connecting to every other point that it has to reach, right? We just use these labels. So in general, this decoder, this multiplexer, like I told you, can be implemented in a more efficient manner. Basically coming here, so what we do in this case is we get rid of this big OR gate, something we already discussed, and okay, and I'm going to now do the following. I'll take my inverter, follow it up with a tri-state inverter. This is I0, right? And this is input Y0. This is I1. So all this, it will go all the way down here. For every single decoder output, I'll do the same thing. This is Y1. This is y2 power n minus 1. This is I 2 power n minus 1. And finally, you just tie all these outputs together. Okay, and you get the y MUX output here. Okay, this is something we had already discussed, so I will not explain this again. However, it is important to understand the difference between these two implementations. Okay, for example, we have this implementation here. Let me put it side by side. Okay, and especially what happens if that input enable is okay. So we have two implementations here. Because because one of these 2 power n outputs, y0 to y2 power n minus 1, one of them is always going to be 1, because we have tied this enable to VDD, right? One of these multiplexers, tri-state inverters, will always be on. Okay, so let me also label the inverters. These are I0, I1, I cannot call it I because I already have it. Let me call it inverter, right? So I will just call it NOT gate, N0, N1, N2 power n minus 1. Okay, and these are my tri-state inverters T0, T1 all the way to T2 power n minus 1. Okay, so what happens is, suppose let's say I had connected this to enable, right? I had connected this to an enable signal instead of 1. Okay, I'm going to assume that case. So if enable were 0 in both implementations, then what would happen is y0 to y2 power n minus 1 would all be 0 in both cases, right? That is very evident. And if you considered the implementation on the left, okay, because y0, y1, all the select lines to the tri-state inverters T0 to 2 power n minus T2 power n minus 1 are all 0, the y MUX will end up floating. This will float if enable equal to 0. Okay. On the other hand, so this is what I call y MUX. On the other hand, the alternate implementation on the other side, right, with that big OR gate, assume that you have implemented this big OR gate hierarchically using smaller OR gates, right? So if that were the case and enable happened to be 0, then y0 to y2 power n minus 1 will be 0, and which means the input to all the AND gates. So let me call these AND gates, let me label them A0, A1, A2 power n minus 1, and this is my OR gate. Okay. So the input to the AND gates A0 to A2 power n minus 1 are all 0. That means Y0 prime, Y1 prime, everything will be 0, and therefore the OR gate output will end up being 0 if enable equal to 0. So this is what I was saying, you cannot differentiate between enable equal to 0 and enable equal to 1, but you know the input which is being selected has its value I0. Let's say enable equal to 1 and all the select signals S0 to Sn minus 1 are 0. That means Y0 will go high, but if I0 happen to be 0, then the Y MUX will end up being 0. You cannot tell the difference in the output of whether the input to the multiplexer is 0 or the enable to the decoder was 0. Whereas in the implementation on the left, the two values you can tell the difference because Y MUX will end up floating at a certain value if enable equal to 0, right? So you could of course this implementation is preferred simply because of the complexity of the schematic being much lesser, right? We just need one tri-state inverter per this thing. There is no huge OR gate that we are trying to implement. We just wire OR that entire output bus, right, and generate the output called Y MUX. Okay.